a handout containing key portions of the presentation that you can use to take notes. You can download it from the handout section on your control panel. And while you're in the control panel in the handout section, download the list of upcoming classes as well. So with that, let's get right into it. Peter, thanks for being here, and I'm going to hand it over to you.
Okay, thank you, Bruce. Okay, hi everybody, welcome. Thanks for joining in today. Hopefully most of you or all of you have been sitting in on the previous two Oscilloscope courses we did back in February and March. So part 3 this time round, and there was a few topics that we were going to cover, but we've had some quite interesting feedback about one part of the presentation that we're doing today. So we're going to focus on one particular part of the presentation, which will obviously cover probably after about 20-25 minutes into the presentation. So you can briefly see me, so good. I can't see you unfortunately, but anyway, thanks for joining again. Let's move on, get into the presentation. The first part I'm going to do fairly quickly, and we're going to start by looking at the basic diagnostic rules that certainly we need to apply when we're looking at this particular part of the presentation, where we're going to be talking about pressure transducers connected to an oscilloscope. And the basic rules really start with 1, you really need to practice. Rule 2 is you need to practice some more, and rule 3, you need to practice even more than that. You'll see why as we go through. We need to be able to grab some good waveforms, some good readings and values before we can make judgment against a bad one. And it'll become clearer as we go through. But fingers crossed, we can absorb it all, and you can get a good feel of how you can use a pressure transducer to do an awful lot of mechanical diagnostics. So everything we've looked at in the previous 2 oscilloscope courses have been based around electrics and electronics. We're going to do a little bit to start with, a little bit more on the electronic testing or electronic systems testing, and then we'll get into the pressure testing and vacuum testing. Okay, with a bit of luck, I'll disappear and we can get on with the presentation, where we're going to look at digital sensor signals. The most obvious one that we bump into on many vehicles is Hall effect sensors. Traditionally, they're used for rotating components, so crankshafts, camshafts, wheel speed sensors. They're also used for positioning of valves occasionally. EGR valves sometimes use Hall effect sensors, but the majority of them really tend to be used for rotating measurements, so crankshaft, as we said, wheel speed and camshaft. As far as I'm aware, all types of Hall effect sensors have 3 wires, 3 connections. We have a reference or a voltage power supply, reference voltage or power supply. We have a ground connection, and we have a signal wire, and all 3 on nearly every system you'll ever come across with Hall effect will be connecting back to the control computer, which I'll just call an ECU, electronic control unit. So we have 3 wires, and using the probe off the oscilloscope, the positive test probe, we can pick up the signal, we can pick up the power supply or reference voltage, and we can pick up any problems we might have with the ground connection as well. So most of the Hall effect sensors you'll deal with typically will have a 5-volt supply, and that by default then creates a 5-volt signal, but the signal, being a digital signal, will oscillate between typically 0 and 5 volts. Sometimes they're just fractionally less than 5 and fractionally higher than 0, but we're going to say it's going to be 0 to 5 volts. There are some out there, not many, but there are some systems, Hall effect systems, where they might be using 12 volts or even battery voltages on occasions. And the thing we need to check with the digital signal of a Hall effect sensor is checking for a frequency change, certainly with speed sensors. So whether that's a wheel speed, crankshaft position or crankshaft speed sensor or camshaft sensor, we need to check the frequency change, and we'll do that by increasing or decreasing the speed of the engine or the wheel. What we do need to do as well is whilst we're checking, especially at the higher speeds with higher frequency signals, what we do need to check is moving the wiring, just change the wiring a little bit, move it around, see if we get any signal drop out. Typically, that tends to happen more when you're looking at the higher frequency signal. And if you look at the example we got here, up the top there, we've got a low frequency signal, and down the bottom, we've increased the speed of the wheel or the crankshaft or whatever it is, and we end up with a much higher frequency signal, so many, many more pulses in the same short period of time. If we don't have a signal, and normally with the oscilloscope test probe, you would go for the signal wire first. That's the usual thing to do. You'll need a wiring diagram in a lot of cases, but you've only got 3 wires to play with here. So one of the 3 should be providing the signal anyway. You won't do any damage by going onto the other wires. So check for a signal, usually 5 volts, as we've said, sometimes they're 12. If you haven't got a signal, you need to check for a power supply, of course, the reference voltage or power supply, which comes from the ECU to the Hall effect sensor. We'll need to check for a good ground connection as well. And ground connection checks we can do with an oscilloscope. I mean, we're not going to cover it today, but in our presentation I'm doing next month, we're looking at series and parallel resistances on vehicle wiring systems. We're going to dig in a little bit there of how to check ground connections using an oscilloscope, which is quite an interesting feature of an oscilloscope, and it does pick up a lot of ground connection faults that you may not normally discover, certainly with a voltmeter or an ohm meter. So that's for about 4 weeks' time. So no signal, check for the reference or power supply voltage, usually 5, but sometimes 12. Check for the ground connection, and then check all the connections back to the ECU. Okay. Another type of wheel speed sensor, or I'll say a rotational speed sensor, but generally they're only fitted to wheel speed sensors, and it's called a magnetoresistive sensor. It's very similar, I suppose, to a Hall effect sensor, but operates in a slightly different way. And if you've ever encountered them, you'll know that a lot of them now, or for many years now, part of the sensor arrangement is actually contained within the wheel bearing. And if you look at the illustration here, you can see we've got sort of red and green sections of a ring, if you like, that's embedded into the wheel bearing. And each of those red and green sections is actually the end of a magnet. It's a positive, north and south poles of the magnet. And as the wheel bearing rotates, those magnetic poles alternately go past the sensor, magnetoresistive wheel speed sensor. And as those magnetic poles, those different magnetic poles alternately go past the sensor, it creates a digital signal, which we can see just at the top there and at the bottom. The magnetoresistive sensors, they're very slightly different to the Hall effect sensor. They normally only have 2 wires, and you'll find that one wire typically has a 10 to 12 volt supply going down to the sensor. So the supply coming from the ECU down to the sensor, and then a ground circuit, obviously, again, back to the ECU. And we can pick up a signal depending on the arrangement of the sensor, the way it's constructed. We can pick up the signal on either the power supply wire or on the ground wire, depending on the construction of the sensor. If we're picking it up on the power supply wire, which we're going to call 12 volts, we get a digital pulse, which we can say is on or off, but it doesn't actually go down to 0. It will start at 12 volts. As we're showing there with my pointer there, it starts at 12 volts, and as the wheel or bearing is rotating, it only drops down about 0.8 of a volt. That's the typical value. So it will go from 12 volts down to just almost 11, back up to 12. So we're still getting a digital signal, but it's not a true on-off pulse. It's just an oscillating voltage between around about 12 volts and just above 11. So that's if the signal is occurring on the power supply wire. If the signal is occurring on what we're showing as the green wire, the ground wire, we still get the same signal, but it's now oscillating between typically about 1 volt and down to almost 0. Again, the voltage change is about 0.8 of a volt. So we can get the signal on either of those two wires, but if it's on the power supply wire, it's typically between 12 and 11 volts, and if it's on the ground circuit wire, it's typically between 1 volt and almost 0. So still carry out the same test procedure, take a positive probe, connect it to the power supply wire, and of course connect it to the ground wire as well. If you get the signal on the power supply wire, that's great, you've got your signal. If you don't get the signal but you've got 12 volts there, then you should get the signal on the ground circuit wire. Obviously, if you've got it on neither wire, then we've got a problem either with the wiring or with the sensor itself. So usual checks, check for the ground circuit, check for the power supply circuit. Okay. Other uses of digital signals, certainly on sensors. Map sensors, now the one I'm sort of highlighting with the pointer there, that's a typical old Ford map sensor from a few years back. And on the right hand side there, we've got the more modern type of map sensor, which is attached directly to the intake manifold. The Ford one used a vacuum pipe connection. But again, they both produce a digital signal. And again, with the ignition on, engine off, you check for a digital signal that oscillates between almost 0 volts and almost 5 volts. So again, we're looking typically at a 5-0 oscillating voltage. If you look at the top waveform there, there's the waveform 0 to 5 volts. And we've said with the ignition on and the engine not running, the intake manifold pressure, therefore, is at atmospheric pressure, and you then tend to get a lower frequency signal. If you then start the engine up and you've now got intake manifold vacuum or low pressure, then the frequency generally increases. So the top illustration would be with atmospheric pressure. So in other words, engine off but ignition on. The lower illustration is what you would normally see when you started the engine up and idle, where you've got a strong pull, a strong manifold vacuum. Again, if there's no signal, check for the 5-volt supply. There would normally be 3 wires on many of them. Check for a 5-volt supply, reference voltage. And if there's no reference voltage, obviously back to the ECU, check the wiring. Again, check the ground circuit with the positive test probe to make sure there's no high voltages on the ground circuit. And again, that's something we'll discuss in about 4 weeks' time. And then start the engine up, as I say, check for a change in frequency as you increase and decrease the manifold vacuum. So if you are at idle, you would have a fairly high frequency, snap the throttle open, and the frequency will reduce because your intake manifold pressure is then heading almost to atmospheric pressure again. So you'll see a frequency change simply by opening and closing the throttle with the engine running. And much the same sort of thing happens with manifold mass airflow sensors. 2 types. You've got the traditional one where it is literally measuring airflow using a heated wire, and there's an alternative version where they have a hot film mounted in the airflow. But they produce the same sort of digital signals. Sometimes these signals are very slightly different. They have a bit of a rounded corner on one or both sides of each pulse, but effectively you're still producing a digital signal. And the voltage ranges typically, okay, we're looking at 0 to 5 volts. Some of them do actually operate on 12 volts. Some of the MAF sensors operate on 12 volts, but so it's either going to be 0 to 5 or 0 to 12. And what we're then looking for, again, as we increase and decrease the airflow going into the engine, we're looking at frequencies on many of them about 2000 hertz, 2 kilohertz when the engine is at idle. So that's with low airflow going into the engine. And it will increase up to round about 8 kilohertz, 8000 hertz, when the throttle is snapped open. So you've got to set the the time scale on the oscilloscope to make sure you can see certainly sort of 10 or 15 pulses to make sure you can see what's going on. Increase and decrease the airflow by opening and closing the throttle, and you'll see the frequency change from about 2 kilohertz at low airflow up to about 8 kilohertz when the throttle is snapped open. Now, some sensors do operate with much lower frequencies, and they're in the range of about 30 to 150 hertz. So not kilohertz, literally down to 30 to 150 hertz. So you'd have to adjust your time scale on the oscilloscope to make sure you could see a good representation of a few pulses. And there are a few sensors out there where the peak frequency might rise actually up to about 12,000 hertz. So depending on which manufacturer has produced the sensor, we could have quite a low frequency, 30 to 150 hertz, or we could end up with a higher frequency, maybe from 2 kilohertz up to as high as 12 kilohertz, 12,000 hertz. Same rules apply. If you haven't got a signal, you've got to check for a power supply, check the ground connections. Then obviously, if it's all working, check the pulse frequencies. And again, play with the wiring, just move the wiring about just to check for a dropout of the signal, which can occur obviously with bad connections. Just one thing to note, there are a few of the sensors, or quite a few sensors out there, where they do have 2 ground circuits. I've seen them with 2 what you will call reference voltage circuits as well, and that's usually because they've got an integrated air temperature sensor that's built into the MAF or the hot film MAF sensor. So you may have 3 wires. If it's not got an airflow sensor, you may have air temperature sensor, or you may have 5 wires if you've got an integrated air temperature sensor as well. But we're obviously more concerned here with the airflow changes. The airflow change causes a change in the frequency. Okay, still with digital signals, looking at something that confuses some people at times, which is pulse width modulation, or PWM, as it tends to be referred to. And one version of pulse width modulation alters what we term the duty cycle. Excuse me, but I'm just going to have a sip of coffee. Now, in the illustration we're looking at here, the digital signal is being switched on and off for different periods of time. At the moment, the signal is switched off for 75% of the time, and it's switched on for 25% of the time. So if we were using this signal to control a solenoid valve, for example, the power supply or the circuit, the current flowing through the circuit, would only exist for 25% of the time. So being very basic about the maths here, we would only have current flow for 25% of the time. Therefore, the current flow would average out at being about 25% of the full value. So if we had just as a simple figure, a 10 amp circuit, 10 amps of current flowing through, because it's only switched on for 25% of the time, we'd only get around 2.5 amps average flowing through the circuit. So if we were controlling a solenoid valve, the valve wouldn't open very far. If we then change the signal round completely, and it was now switched on for 75% of the time and switched off for 25% of the time, we would now have current flowing through the circuit for 75% of the time, which means we would now, on our theoretical circuit with 10 amps, we would now have 7.5 amps average current flowing through the circuit. So again, if it was connected to a solenoid valve, the valve would open much more than if we were switched on for 25% of the time. So changing the on time increases the average current flow passing through the circuit, which means we can open and close a solenoid valve, we can control an electric motor, increasing and decreasing the duty cycle, the on time, if you like, for an electric motor, can provide more torque on that motor, effectively ends up changing the speed. And we don't use this very often on sensors, but it's certainly used on controlling actuators such as solenoids and electric motors to control how fast the motor may be turning, how much the solenoid opens up a valve. It could be an air valve or a fuel pressure control valve. Even the old EVAP solenoid valves, some of those were controlled using digital signals with altering the duty cycle to increase and decrease how much the valve opened. So here's an example of a solenoid controlling an air valve. Again, in the left-hand illustration, the circuit has a pulse width modulation or a duty cycle where it's 75% off, 25% on, and that means that we've only got an average current, and let's say the full current was 10 amps, we've only got an average current of 2.5 amps. It's not exactly true, but it's close enough to be able to illustrate what's going on. So if we've only got a low current going through, a low average current going through the solenoid windings, the valve will only lift slightly, and therefore we get a small amount of airflow through that valve. That could be fuel pressure control valve, but in this example, we're looking at airflow control. In the right-hand illustration, we're now switched on for 75% of the time, so we're going to get much more average current flow. In theory, we would have our 7.5 amps if it was a 10 amp circuit, which means the solenoid winding is getting a higher average current flow. The solenoid will rise further up, which means it will open the valve farther and allow more airflow to flow through. Now, this happens thousands of times a second, so we're not just seeing this happen every so often. This is happening thousands of times a second. So the valve will tend to adopt a position that is dependent on how long the on time is compared with the off time. The greater the on time, the more energy or more electrical power is flowing through the solenoid winding, the higher the solenoid will go and open the valve more. So it's controlling solenoid valves. It can be an electric motor, and one example that's very common nowadays is the fuel pump on vehicles, where the fuel pump speed is controlled by changing the pulse width or the duty cycle of the signal that's being passed to the fuel pump. So it's not just solenoid valves, it's electric motors, and the pulse width modulation is also used, just as an example, on electric vehicles to control, partly control the speed of the motor. Okay, another part of pulse width modulation is where we actually control the on time specifically to a value that will, in this example, control how long an injector is open or closed for. Now, when we looked at the previous example of a solenoid, we actually looked at a positive circuit being switched, but in reality, most electronic control systems control actuators on the negative circuit. So we end up with the on period being at 0 volts and the off period being at battery voltage. But in this example, looking at an injector, when the engine is idling, we may not want too much fuel to pass into the engine, so we have quite a short period where the injector is switched on. So in this example, 2 milliseconds, 0.002 of a second. But if we wanted to inject a higher quantity of fuel, maybe we snap open the throttle, place the engine under part load, we want to increase the on time of the injector, so that pulse width is now increased in this example to 5 milliseconds, 0.005 of a second. And you can test that quite easily, again, using the oscilloscope positive test probe onto one of the injector terminals. One will give you the power supply, the other one will give you the signal, and literally start the engine, snap open the throttle, and you'll see the pulse width change as you change the load on the engine, which obviously will demand a different quantity of fuel to be injected. So you'll see a change in the pulse width simply by opening and closing the throttle. So it gives you an indication what's going on. And again, as with all of the examples we've been looking at so far, what you need to do, of course, is get some good samples. Now, some of the diagnostic equipment manufacturers, the oscilloscope manufacturers, have their own libraries, and they're handy. It's a good start point. But whenever you get the opportunity, just hook up to a good car. If you've got an oscilloscope that allows you to save the images, maybe even print them out. Do as many as you can, because you can't really tell a bad one until you've seen a good one. Okay, let's get on to the quite an interesting aspect of using an oscilloscope, and this is where we get pressure signals, and for that we need to pick up pressure transducers. Now, I think most of the oscilloscope manufacturers now supply as an option or as an accessory pressure transducers, but there are some aftermarket versions out there which allow you to detect pressure, and whether it's from the manufacturer or whether it's an aftermarket version, that pressure transducer will convert the pressure changes into an electrical signal. Now, ideally, if your oscilloscope that you've got or going to buy, if the manufacturer produces also or sells also a pressure transducer, then it's most likely that that transducer will provide a calibrated signal to the oscilloscope. And using the options on the oscilloscope, you can actually select then a pressure scale. So when you hook up your pressure transducer, and we'll look at different ways of hooking it up in a moment, but when you connect the pressure transducer, what you should therefore be able to get is a pressure value, pressure measurement displayed on the oscilloscope. Now, some of the aftermarket pressure transducers, you may not be able to get an exact calibrated pressure value. It will give you a voltage value. Now, sometimes they will actually say a certain voltage equals a certain pressure. So 1 volt on your oscilloscope, if it gives you a voltage value, 1 volt could equal 10 psi, 100 psi, or whatever. So at least you get a start point where you can get a rough idea what the pressure is. But with pressure testing, a lot of the diagnostics that you do with pressure waveforms is actually comparison from a good cylinder to a bad cylinder. And we'll look at that as we go through in a few moments. So ideally, if you can get a pressure transducer that will connect your oscilloscope and give you a pressure value, that's the best route. But if needs be, get a pressure transducer from an aftermarket source, and that may give you the voltage reading, but in a lot of cases you can then convert that voltage reading into a pressure value. There's a couple of different types of pressure transducers. By preference, if we can get one with obviously the calibrated values, that's great. There are some sensors that only provide, they term it a pressure differential. And what it's going to show you is any increases or decreases in pressure that exist, whether that's in the cylinder or in the intake manifold, but it gives you a pressure differential. And that's still very valuable because you can still see the changes in pressure, and you can see a good one versus a bad one. Okay, when we're testing with pressure transducers, if we're doing cranking tests, so we don't want the engine to start, obviously we need to disable the fuel injectors wherever possible, because the last thing we want to do is inject fuel into the engine. If we're just doing a cranking test, we don't want to build up an excess of fuel in the cylinders. If you've got a carburetor vehicle, you've obviously got to disconnect the fuel line and make sure the carburetor is empty before you start the cranking test. And ideally, we want to run a cranking test for at least 5 to 10 seconds so that we can get some consistent results. And in most cases, we want to try and be able to do a cranking test with the throttle open. Some of the tests we can do with the throttle closed, but quite often you want to do it with the throttle open. If we then start up the engine and we're doing an idle test, for each cylinder that we're testing, so if we're now doing in-cylinder tests where we've taken out the spark plug, and attach the pressure transducer to the spark plug hole, what we then need to ensure is again that we disable the fuel injector, because this cylinder isn't going to be running. We've taken the spark plug out. Again, the last thing we want to do is fill the cylinder with fuel. And because we've taken the spark plug out, our coil is now disconnected. If it's a coil on plug system especially, we need to ground the high voltage output from the ignition coil, or disconnect the harness that's switching the coil on and off, because we don't want to burn out the coil. So we need to ground it or disconnect the harness, and of course that could set a trouble code, so you might have to reset that afterwards. But with all the tests we're going to look at, we need to compare values, if available, with a known good example, and we need to compare the pressure waveform shapes, and we'll look at those shapes as we go through the next few slides. So for the first test, we're going to look at in-cylinder pressure testing. And again, we're going to take the spark plug out, attach a hose to the spark plug hole, and then attach our pressure transducer, our pressure sensor, to the hose. And that will connect to the oscilloscope. And if we do a cranking test, we will create cylinder pressure while we're cranking. We're not going to get full pressure, of course, because we haven't got any combustion going on at this particular stage in the process. So we've got a dead cylinder. We're just going to get the pressure that's building up and then falling off as the piston is rising and falling in the cylinder. So for a cranking test, obviously we're only going to be cranking at 150, 200 RPM, and that's actually quite a long time for an engine. And in that fairly long time, it does allow the cylinder to fill during the induction stroke, and that's even with the throttle closed, because it's cranking so slowly. The downward movement of the piston does pull in quite a bit of air, so it almost fills the cylinder. So you do get quite a high pressure even with the throttle closed when you're doing a cranking test. Now, ideally, we open the throttle because that gives you a better idea of what the highest pressure level is going to be in the cylinder, certainly under cranking. And in the example we're showing here, we're looking in the region of about 150, maybe up to 200 psi during cranking. And that's partly because we're going so slow and there's plenty of time for the cylinder to fill up. So ideally with the throttle open, you'll get certainly, we always used to say 150 psi was a good figure. Modern engines, especially with the high compressions that they're now running, you can actually get in excess of 200, and there are some where you might even be as high as 300, even under cranking. So quite surprising the pressure you can build up. So again, you have to get some good examples of different types of engines just to get a feel of the sort of pressure levels you're going to get. But certainly 150, maybe 200, maybe even 300 during cranking on the more modern engines. So that'll give you a cranking peak pressure. If we then start the engine up, and again, don't forget this one cylinder that we're testing is disabled, it's not producing any combustion. So the engine is now going to be turning a lot faster than during cranking. We're going to be running at maybe 800 RPM, something like that, 750 RPM. So the engine's turning a lot faster than during cranking. There is less time to fill the cylinder. And what that means is that the pressure is actually lower at idle, because don't forget the throttle is now fully closed. So it's acting as a massive restriction to incoming air. So although the piston is traveling down the cylinder, pulling in air, it's got this horrendous restriction that we call a throttle, stopping the air coming into the cylinder. So we don't build much pressure up when it's on the compression stroke. So idle with a closed throttle, we typically get in the region of 60, 70, 80, 90 psi on the compression stroke. So cranking is a higher pressure than you actually get at idle, because at idle we've got a totally closed throttle and we've also got a much higher speed, so there's less time to induce a high volume of air into the cylinder. But if we then snap the throttle open, the moment you snap the throttle open, of course, there's no restriction, there's no throttle restriction, so we can now draw in the full amount of air into the cylinder. So the cylinder pressure with the throttle snapped open therefore rises up to pretty much whatever the peak is going to be, and that can be 200, again up to maybe 300, depends on the engine, depends on the compression ratio, and a few other factors. So no throttle restriction. When you snap open the throttle, you get much higher pressure, and that's a good indication of whether the cylinder is filling up properly, and the compression is good. And we can look at a bit more detail as we go through to the next slide. So an induction stroke, certainly if you're cranking on the induction stroke, we're pulling in air. We have got the throttle, which is acting as a restriction. So during cranking, cylinder is disabled again. Don't forget, we're not going to hit any combustion here at all. Cylinder is going, or piston is going down the cylinder. We're pulling in air against that restriction of the throttle butterfly. So we're only going to get a low pressure here, 60, 70, 80, 90 psi. And the pressure in the cylinder, when the piston comes down to the bottom, so at the bottom of the induction stroke, the pressure will have dropped down, it's actually a negative pressure, to about -9 psi. If you're using the traditional measurement, which was inches of mercury, 9 psi is about 18 inches of mercury, 10 psi is about 20 inches of mercury. So 9 psi, just double it, and that will give you your inches to mercury, give or take a fraction. So when the cylinder is coming down, the pressure initially, just before the cylinder or the piston starts to move, will be at atmospheric pressure. As the piston comes down the cylinder, it will pull a vacuum. Shouldn't really call it a vacuum, but we do. It will pull a low pressure, which will drop down to typically 9 or 10 psi, something in the region of 18 to 20 inches of mercury. So we pulled the vacuum, we'll use the term vacuum, we pulled a vacuum, and then the piston will start to rise on the compression stroke. And at the end of the induction stroke, just after the end of the induction stroke, the inlet valve closes, the piston starts to rise, and therefore the pressure in the cylinder will start to build up, and it will build up and up and up until we hit this sort of peak. And this could be our 60, 70, 80, 9 psi if we're cranking. If we're running the engine, that pressure, remember we said on the previous slide, that pressure will rise. Sorry, I'm calling this idle. This is actually running. I beg your pardon. 60 psi when the engine is running, not cranking. I'm sorry. Don't want to confuse you here. So we're at idle. The throttle butterfly is closed. So we're rising up to about 60, 70, 80, 90 psi at idle. Now we've got what we're going to call a power or expansion stroke. We're not producing any power because again, the cylinder is disabled. But the moment we reach top dead center, we reach our peak pressure, our 60, 70, 80, 90 psi when the engine is idling. The piston then comes down on what would have been the power stroke, but we're now going to call it an expansion stroke because we've squeezed the air, we've compressed the air up to the peak pressure, and now the piston is coming down. So that same piston, or that same volume of air, is now going to expand again as the piston comes down and opens up the cylinder again. So the pressure now drops down, and again it will go back to pretty much where we started. It will go beyond 0 psi or beyond atmospheric pressure. It will go down to our vacuum level again, our low pressure level, 9 or 10 psi, once the piston reaches bottom dead center. So idle, we reach about 60 psi, 70, 80, 90 psi at idle in this cylinder. The piston comes down on the expansion stroke. And as the piston reduces, it opens up the volume in the cylinder again, and the pressure now drops down once again to about -9, -10 psi, or 18 or 20 inches of mercury. at which point the exhaust valve then opens. And we should be getting the exhaust valve opening here. There we go. The moment the exhaust valve opens, although we've got this negative pressure, this low pressure in the cylinder now, the moment the exhaust valve opens, because the exhaust system is exposed to atmospheric pressure, the pressure in the exhaust pipe is actually atmospheric pressure. Therefore, when the exhaust valve opens at the end of the expansion stroke, we now expose the cylinder to the pressure that's in the exhaust system, which, as we've said, is atmospheric pressure. So as the exhaust valve opens, atmospheric pressure is effectively pouring into the cylinder that was at a low pressure or a vacuum, and it will now rise up to about atmospheric pressure, especially once the piston starts to rise and force the air out of the cylinder on the exhaust stroke. So again, don't forget, we haven't created any combustion, so we're just at normal negative pressure here. We open the exhaust valve, atmospheric pressure from the exhaust system enters the cylinder, so the pressure rises in the cylinder, and as the piston rises up the cylinder, the air is forced out past the exhaust valve, and as it does so, it oscillates slightly as it's going past the valve, until such time as the inlet valve then opens again, and we start the whole process again. So the inlet valve opens, and the moment the inlet valve opens, we're now exposing the cylinder again to the intake system, and the cylinder piston again starts to fall down. So the moment the inlet valve opens, that's the last peak we will see of any pressure rise. And there's something just sort of keep in your mind there. The inlet valve opening, that's the stop of any pressure, or the end of any pressure being produced on that exhaust stroke. So the moment the cylinder reaches TDC and the inlet valve is now opened, piston comes down again, and we once again produce a negative pressure, or a vacuum, if that's what we want to call it. And those numbers there, which I think you've got this on the handout, guys, the numbers there are just the key areas we need to look at on an in-cylinder pressure check. So number one, obviously, is where the pressure falls to a negative pressure or a vacuum. Number two is where the inlet valve closes, the piston starts to rise past atmospheric pressure at 3 and up to the peak pressure at 4. And then when we get to 5, the piston is on its way down again on the expansion stroke. So the pressure is now falling down, and it will stay down at a negative pressure until the exhaust opens, and then we expose the cylinder to atmospheric pressure from the exhaust system. We get a few small pressure oscillations until the inlet opens again, and once the inlet opens, we start the whole process all over again. Okay, moving on, see if we can pick up a couple of problems. Right, we've got a dotted red line here. When that dotted red line occurs, we're actually showing it at a slightly higher pressure than what we would expect to see. We're expecting to see -9 psi, pulling a vacuum of -9 psi. And in this example, we're probably at about 5 psi there, something like that. In other words, we're not pulling such a strong vacuum, we're not lowering the pressure as much as we expect to see. And that is due usually to a poor intake vacuum, and that can be leaking valves, it can be a warm piston, rings and bores, effectively anything that's stopping that cylinder from sealing properly. So leaking valves, pistons, rings, bore wear, anything like that, and it will stop the vacuum going as low as we want it to go. And the same thing would apply then when the piston is going up on the compression stroke. As the piston is rising, the pressure, which is already or the vacuum, which is not as low as we expected it to be, so we've got a slightly higher pressure, And as the piston's rising and rising and rising and rising, the pressure will try and escape if we've got a leaking valve, warm piston, rings and bores and so on. Okay. Right, so we've got reduced vacuum. We haven't got the low pressure that we expected because of leaking valves, warm piston, rings and bore and so on. And then we go on to the next phase that we're going to look at, which is the exhaust stroke. And if the piston is rising, we'd expect to see the pressure in the cylinder go up to atmospheric pressure. But in this example we're showing here, it's actually gone above atmospheric pressure. Now, remember what we said, the moment the exhaust opens, the pressure in the exhaust system will enter the cylinder, and the pressure in the exhaust system is atmospheric pressure. And if the pressure that we see is higher than atmospheric pressure, that's usually an indicator that the exhaust system has a blockage. Now, that typically could be a blocked catalytic converter, so block cat. And what you tend to see when you get a blockage in the exhaust system, once the exhaust valve opens, instead of the pressure being at atmospheric pressure, the pressure actually starts to build up and get higher and higher as the piston is rising up in the cylinder. So we're forcing air out of past the exhaust valve into the exhaust system, but the exhaust system is blocked, which means we're ending up with a higher pressure in the exhaust pipe and therefore in the cylinder. So if you see that sort of waveform, it's the right shape, but it's increasing and increasing and increasing. It's starting higher and increasing simply because we've got a blockage in the exhaust system. It will affect then the pressure when the piston is again on the induction stroke, because we're already starting with a higher pressure. We're just not going to pull a vacuum if we've got pressure in the exhaust system. So we've got inlet is open. We're trying to draw in air, but we've already got pressure in the cylinder, because when the exhaust is open here, between the inlet opening and the exhaust closing, we've got a higher pressure, so we won't pull as much vacuum, and that generally means that you probably won't produce as much peak pressure either. So looking at the blue trace, which is our expected pressure, we won't get atmospheric pressure with the blocked exhaust. We'll get a higher pressure on the exhaust stroke. We'll get a higher pressure normally on the induction stroke. We won't get the full vacuum, and there's a good chance we'll actually get a lower pressure on the compression stroke as well. Just another way you can use the peak pressures, just an example here, what I've done is taken pressure values from an 8-cylinder engine. It could be obviously a V8. Now, you would need 8 pressure transducers in each of the cylinders to do this test, but if you've got an oscilloscope where you can save each measurement, you could do a test on each of the 8 cylinders and then bring those saved values back onto the screen so that you can make a comparison. So each of these, that cylinder, a cylinder off of bank 1, there's a cylinder off of bank 2, cylinder off of bank 1 again, and so on. So I've just overlaid the 8 different waveforms in a line so that we can see a comparison. And what we've got here is bank 1 going high, bank 2 going low, bank 1 going high again. So this is in firing order, whatever the firing order on this engine might be. And what this is showing us is that always on bank 2, we're getting a lower pressure value. And there's a good chance, therefore, that bank 2 has a blocked cat, but bank 1 doesn't. So we're getting a pattern, we're getting a trend that we can see. Bank 2, each of those bank 2 values is low. Now, you can't always do this with the oscilloscopes. You can't always get the 8 cylinders side by side. But obviously, if you're testing all of the 8 cylinders, you can note the measurements. And when you note the measurements, you can make the comparison just to see if those cylinders are even, or if you've got one bank that is worse than the other. Now we're now looking at one cylinder, cranking on one single cylinder. It doesn't matter which one, could be number 1, number 7, doesn't matter. And we're seeing a pressure variation on this one cylinder. Whilst we're cranking, you could get the same thing while you're running. You could get this high pressure, then a low pressure, high peak pressure, low peak pressure, and so on, which in theory, of course, shouldn't happen because you're looking at just one cylinder. You're looking at one set of inlet valves, one set of exhaust valves. Nothing should change. But it is. We're getting high pressure, and then a little bit later, we're getting a low pressure, some high pressures, low pressures, and so on. And what that usually indicates is that one of the valves, and you have to think of the way a valve works. Obviously, it opens and closes, but all valves designed, the mechanism, the valve train mechanism is designed so that the valve rotates while the engine is running. So it just partially rotates each time the valve opens and closes. And what can happen is you get a little bit of wear or burning or whatever on the valve seat or on the seat in the cylinder head. And as the valve rotates, there it's making a good seating. But as it goes down to the lower pressure, the valve has rotated slightly and perhaps picked up on a bad part of the valve seat. So we get a slight leakage, and so we get a lower pressure during the compression phase. So high pressure then low pressure on the same cylinder usually indicates that you've got a valve seating problem. Okay, try and give you another few examples, I think. Okay, so got to remember that the spark normally occurs just before top dead center, just before the power or the expansion stroke. And again, this could be cranking or idle, it doesn't matter. On a disabled cylinder, so we're measuring cylinder pressure on the disabled cylinder. And if we use the second channel on the scope, and most scopes have a second channel, if we picked up a spark timing signal, now that could be secondary waveform, primary waveform, or even the current waveform picking up off the ignition coil, what we can then do is use that spark timing signal to synchronize the waveform of the spark against the cylinder pressure waveform. So spark occurs just before top dead center. So we've got compression, then the spark occurs just before top dead center, or the end of the compression stroke, and we then get our power or expansion stroke. And we've now got it synchronized. So what we can now do is try and work out what happens if we had a change in the ignition timing. Now, it's not a desperately common problem, but we do get problems where the timing reference signal is obviously on the crankshaft, can be on the front pulley, and sometimes you get front pulleys where the keyway breaks. For whatever reason, the front pulley is incorrectly set on the crankshaft. Now, if I just go back again, we know that the spark should occur just before top dead center. But if the pulley is incorrectly positioned and the timing reference is incorrectly positioned, then there's a good chance you're going to get the spark occurring after top dead center. So what you can see here is that we're synchronized to the spark plug, to could be number 1 or whatever, and we see that the spark is occurring after the peak pressure rise, and the peak pressure rise occurs at top dead center. So we've now got delayed timing. And I guess probably most of you don't usually check timing or ignition timing. We don't use timing lights anymore like we used 2 years ago. So generally speaking, we don't check ignition timing as a rule. And that's one way of checking ignition timing. If you've got an engine performance problem and you do a cylinder pressure check, just check that the timing is where it should be and not delayed as we're showing in this example. Okay, another thing that we can come up with. Now at the moment we're showing when the inlet opens, when the exhaust closes. We're looking at our 7 key points of reference for our pressure rises and vacuum. But if our inlet timing is incorrect, and we could have a slack timing chain, or the camshaft might have jumped a tooth, the belt might have jumped a tooth, timing belt, we could end up with a delay in the inlet opening. Now, remember a little bit earlier, let me just go back again. Remember, we get our atmospheric pressure once the exhaust valve is opened. So whatever pressure is in the exhaust system is now exposed to the cylinder. So once the exhaust valve opens, so we're now exhausting the air out past the exhaust valve. It goes out in a little small series of oscillations, and at 0.7 there, that last little pressure peak, that occurs just about the time that the inlet valve opens. And once the inlet valve opens, of course, then we've exposed the cylinder now to the incoming air that's going to happen as the cylinder goes down. So that last pressure peak occurs just about the time that the inlet valve opens. But if our inlet timing is incorrect, that pressure peak will now occur after bottom dead center, after top dead center. That pressure peak occurs, or should occur, just before top dead center when the inlet valve normally opens. But if that pressure peak, that last pressure peak, occurs after top dead center, that usually means that your inlet valve opening is retarded, and so of course will be your inlet closing. So inlet valve timing, you can pick up if that peak is after top dead center. It should be just before. The inlet valve should open just before top dead center. If it's opening after, then there's a good chance your inlet valve timing is retarded. Okay, next possible diagnostic problem is if our exhaust valve is retarded. Now, that can happen again with timing belts and timing chains. And you might, on a lot of engines, you might have had a camshaft timing reference signal on the inlet camshaft, and on some of the slightly older engines, you may not have had it on the exhaust camshaft. So what happens again is the exhaust valve opens here. Remember, on the bottom or the downward stroke, the expansion stroke, the exhaust valve opens just before the piston reaches bottom dead center, and the exhaust valve closes again when the piston is on its way down on the induction stroke, at the bottom of the induction stroke. Now, have I got that wrong? The exhaust valve closes, yes. So after the exhaust stroke, then the exhaust valve closes. But if you've got retarded timing, maybe because of a slack timing chain or jump to tooth on the belt, what you tend to find then is you don't pull the vacuum in the cylinder on the induction stroke, because the exhaust valve is open later. So you're trying to pull a vacuum, but you can't because the exhaust valve is still open. So you're pulling in pressure from the exhaust system. So if on the induction stroke you're not pulling in a good vacuum, there's a good chance now that your exhaust valve timing may be delayed, may be retarded because of a slack timing chain or because of a jumped tooth on the belt. So again, it's one of these things you've really got to get a good waveform to be able to make a comparison with the bad one, but at least you're getting some ideas now of the sort of things you can check with cylinder pressure. We're pretty much coming up to the hour, but we've got perhaps going to just 2 or 3 more slides in. We're going to look here now at intake manifold pressure. So we've now got our 4 cylinders, 8 cylinders, whatever, all connected up, all running. And what we tend to forget occasionally is that with most 4, 6, 8 and 12 cylinder engines, there are always companion cylinders. So on a 4 cylinder engine, 1 and 4 go up and down together, and 2 and 3 go up and down together. So when one cylinder is on the power stroke, the companion cylinder will be on the induction stroke, both cylinders or both pistons going down. And then when one cylinder is on the compression stroke, the companion cylinder will be on the exhaust stroke. Now, if we hook up to the intake manifold using our pressure transducer, we will get something similar to this. We will get a pressure waveform, which initially doesn't make an awful lot of sense, other than the fact that when we are on the intake stroke, we will get a lower pressure. So all of these lower peaks are based on intake pressure during the induction stroke. We're getting a negative pressure on the intake stroke. So lower pressure at the bottom, or we can call it a vacuum, and atmospheric pressure at the top. Now, if we're running the engine, yes, we'd say it'd be atmospheric pressure at the top, but if it's a turbo or supercharged engine, then you could have higher pressures there. But we'll stick with a non-turbo, non-supercharged engine for this. So atmospheric pressure at the peak, and a low pressure or vacuum at the lower peak. Now, in reality, if you hook up a pressure transducer, the waveform might actually look more like that. You will see some really strange and lumpy waveforms, but you can still see that there is a lower peak there, lower peak there, lower peak there, although it's not a very low peak, that one. We'll come back to that in a minute. But there's the lower peaks, if you like, the low pressure or the vacuum signal. And we're not going to worry about the upper peaks for a minute, because they will actually make no sense at all, other than the fact that we're not on an induction stroke when we get the higher peaks. Now, what we then need to do is try and figure out which of those peaks and troughs, which of those low pressure vacuum signals corresponds to which cylinder. And again, we want some sort of synchronization. So I'm using as an example cylinder 1 spark. So we're hooked up to the second channel on our scope to the ignition system in some way, so that we get a spark reference. So that's cylinder 1 sparking there. On a 4-cylinder engine, we will get 4 peaks and troughs, and then the next cylinder will spark. So there's our 4 cylinders. It could be 1, 3, 4, 2, and then number 1 starts again. So there's our theoretically good waveform. Okay, atmospheric pressure at the top, low pressure at the bottom. There's our cylinder 1 spark there, and cylinder 1 spark there. So there's our 4 cylinders. And it's still really trying to figure out which of those troughs corresponds to which induction stroke on which cylinder. And it's probably fairly easy to work out on a 4-cylinder engine, but if you've got a 6 or an 8 or a 12-cylinder engine, it's a nightmare to try and figure it out. And there is a nice way of doing this. There is a free download, which I've just shown, I think, on your handouts. You've got that message there. It's what they call a pressure waveform overlay. There's 2 or 3 different versions out there, but the one I'm going to show you right now, it's an overlay you can download. It's free. If you've got a computerized oscilloscope, so if you're running something like a Pico where it displays on the computer screen on the computer, I believe you can actually overlay this this image onto the scope screen when you've got the waveform running. Maybe wrong, but I'm pretty sure you can. But normally, if you've just got a conventional scope that's not displaying through a computer, what you tend to need to do is copy and paste the waveform and then overlay it onto this this free download, this pressure waveform overlay. You can overlay it, so if you've got your manifold pressure and vacuum waveform there, plus on the second channel you've got your spark, overlay, copy it and overlay that onto the overlay app that you've downloaded. And what you will then be able to do is adjust the size of the overlay so that it matches cylinder 1 sparking there, and the end of the overlay now should line up with your cylinder 1 sparking there. And you can set the overlay for whatever number of cylinders, whatever the firing order, and whatever timing reference you're using. So you had an 8-cylinder, you can put in 8 cylinders, put in the 8-cylinder firing order, then tell it which spark reference you're using, number 1, number 5, number 8, doesn't matter. And what you will then get is the different strokes that occur whilst the engine is running. So we've got a 4-cylinder engine here, easy one to use, but we've got cylinder 1 is sparking there. Okay, so there's our initial reference. Cylinder 1 is at the bottom, so cylinder 1 sparks. We then go on to the power stroke on number 1, but there is a induction vacuum there. We've got a low pressure there, that's induction. But which cylinder is it on? It's actually on number 4. So if the piston on number 1 is going down on our power stroke, then cylinder number 4, its companion cylinder, is going down on the induction stroke. Okay, so the overlay helps you work out which cylinder is on the induction stroke, which cylinder is on the exhaust stroke, and so on. As I say, just search, go onto the internet, just search for pressure waveform overlay. You can download it. It's only a small file, and it's really handy, especially if you've got multi-cylinder engines, 6 or 8 cylinders, because it's very difficult then to work out which cylinder is on the induction stroke. So now we can say that that's induction stroke for cylinder number 4. Okay, so there's our trace, there's our waveform, induction intake manifold waveform, atmospheric pressure at the upper peak, and our strong vacuum at the lower peak. There's our second channel coming in. It could be the primary ignition signal, secondary ignition signal. This is our synchronizing signal. We could be using a current waveform off the ignition coil as well, whichever way you want to pick up a timing reference. And after the spark occurs on cylinder 1, the cylinder will pass through the power or expansion stroke. Therefore, cylinder 4 is going to be on the induction stroke. So we said it just now on the previous slide. So although we're looking at spark timing maybe for number 1, it's number 4 that's on the induction stroke there. Now I've sort of created my own little overlay here. So there's our sparks occurring on the different cylinders. This is the basic principle of that overlay. So there's a spark for number 1. So the cylinder will now go down on its power expansion stroke, which means number 4 is on the exhaust stroke. If we were using spark number 3 as our reference, okay, cylinder number 3 will then go on the power or expansion stroke, which means cylinder number 1 will be on the exhaust stroke, and so on. And that's how you use that overlay to decide what's going on in the waveform, which cylinder that waveform low pressure corresponds to. Just makes it an awful lot easier. I've just highlighted this little bit here for a moment, just another example of a possible problem, and this is probably going to be our last slide. You'll see this slightly flattish peak here, and that's occurring when the inlet opens and the exhaust closes on this particular cylinder here. And I've seen this a few times, and this is often an indicator that you've got a worn cam lobe or a worn cam follower. Something's not quite right with that camshaft lobe, and whether it's on the inlet or exhaust, you'd have to examine. But that sort of slightly flattish trend, when all the others are fairly rounded, that slightly flattish trend with the sort of almost corners on it can be an indicator of worn cam lobe or worn cam follower. And I think just the next one will be our last one. In this example, it happens to be cylinder 2 there. It's producing less vacuum. So there's a vacuum on cylinder 4. There's a vacuum on the induction stroke on cylinder 1. But there's a vacuum or induction on cylinder 2, and it's less. And now, fairly obvious, if you've got poor vacuum on one cylinder, it can be caused by badly seated or burnt valves, warm rings, warm bores, etc. So what we're really looking at is using intake manifold vacuum, using all the other waveforms we looked at in cylinder pressure testing as well, just to try and pick up whether the vacuum on the induction stroke for each cylinder is good. And if we ran the engine for a few seconds, froze the waveform, and we saw this repetitive weak vacuum on a cylinder, that happens to be number 2 again here, okay, we can certainly guarantee that number 2 is giving us the problem, could be causing a misfire because we've got a very weak vacuum. Here's a good vacuum down low here, and there's a bad vacuum there. So you can do this comparison of all the cylinders. It happens to be number 2 in each case here, so we know we've got a problem with number 2. If you've got a problem with 2 adjacent cylinders, so say you had 2 and 3 on a 4-cylinder engine, if they were low vacuum, you could have a leaking head gasket across those 2 cylinders. Yeah, you depending on the trend that you see, that will dictate what sort of problems you've got in the engine, and it can give you an indicator whether it's on 1 cylinder, a pair of cylinders, a bank of cylinders, and so on. So it's an awful lot to take in. Again, I would stress you do need to do as much practice as you can, but hopefully you've sort of gained something out of this one, guys. It's well past time, so I need to wrap up, but thanks for staying with us. Thanks for joining in.
All right, thank you, Peter. Yeah, there's a lot of info here. I could spend another hour on it, but unfortunately we don't have it. But thank you for sticking with us today. Thanks, Peter. If you have any further questions about today's class, you can send us an email at wti@worldpac.com and include the class number in the subject line of your email. Today's class is LTT 503. And take a few minutes to fill out the survey. We are scheduling classes. We listen to what you're saying, what you want, your comments, suggestions, and would like to provide you with the training that you need. So with that, thank you again. And this webinar is now ending. Thank you, Peter.
Okay, thanks.